Good morning, everyone. It's 10 o'clock on the East Coast of the United States. My name is Matt Baker. I'm the Director for Critical Power and Microgrids at Typhoon. And we're excited this morning to go over our latest 2020.2 Typhoon HIL Control Center release. Appreciate everybody being here this morning. This is the first time we've done one of these webinars on our Control Center update, and our hope is that this will be an interactive morning where you get a chance to ask questions in addition to getting information. It's a small group by design, so please use, if you look at your control panel for the webinar, there's a chat line, and if you open that and send your questions, that's the best way for us to get them. But even if you have one while we're talking, please raise your hand and we'll do our best to get to you as this unfolds. What I'm going to do initially, just while we wait for people to kind of close up, we've got about 35 attendees right now. But what I'd like to do is start out with a poll to kind of find out a little bit about you and where you're from in the world as you sign in. And I wonder if you would please just take a couple minutes to check where you're coming from so that I can, in addition to introducing the Typhoon team, introduce you all. Looks like as this unfolds, we've got some folks from the Asia Pacific area, Latin America, the Middle East, Europe, and North America. So all 5 regions are covered. Very nice group of people. Looks like Europe is slightly going to edge out the North America contingent with about 48% from Europe and 40% from the US. I'll give it a couple more seconds as people show up. This is kind of our way of introducing the crowd, and I'm going to introduce the Typhoon participants here in just a moment. So I'm closing it up, but you can kind of see 48% of participants are from Europe, 40% from North America, and we've got nice representation from Asia, Latin America, and the Middle East as well. So thank you all, and we'll get back to the brief. So you've got 4 panelists, if you will, this morning. I've introduced myself. I'm very pleased that Dusan Mastrovic is with us. He's the Chief Technology Officer for Typhoon HIL. We have another Dusan, who's our modeling team expert. And then Petar Gardner is our head of the modeling team. So we've got 2 representatives from there. This is our agenda, and without further ado, I'm going to shift you over to Dusan for the presentation. But again, I want to reiterate, and we'll do one more poll as we shift over. I want to reiterate that there are there's a way to ask questions in the chat. And the last thing I want to point out is if you would like, there's a handouts button that's very, very useful in this webinar format, and you can download all of the slides that we're going through today. Finally, we'll be recording this event. There will be a recording if for folks who weren't able to dial in. And the last piece, we'll remind you of this one more time, is that a survey will come out right after we end today, and it'll be delivered to you by email. And I really ask that you pay attention to that. Like I said, this is the first time we've held a webinar, an interactive brief on our 2020.2 highlights and updates. And we're excited about this new format, but we need you to tell us how to make it better. I'm going to go ahead and close the survey, and very interesting. I'll share it with the crowd real quick. 51% PV solar, 43% drives, 34% EV automotive, energy storage battery at 43%, and 74% microgrids. Clearly there's some overlap there. People are checking multiple things, but I think you all are all in the right place. And with that, I'm going to hide the poll, and I'm going to shift the presentation over to Dushan. So Dushan, you should have the presentation now.
So thank you, Matt, and it's a great pleasure to be here. So, but Matt, at the moment, I still do not see the option actually to share my screen. So. Oh yeah, here it is. So thank you, Matt, and I hope that you can all see my screen now. So yeah, our today's agenda, as we already mentioned, we're going to start with short 2020.2 feature highlight walkthrough. So I'm going to take this part for around 15 minutes. And then we are going to move on to the more interesting part today. We're going to have two demos. With the first demo, Peter is going to show and tell us more about new addition to our advanced machine models. And this demo is going to be followed up by the demo presented by my colleague Dusan Čohnačić, who is going to demonstrate the usage of our latest addition to the microgrid library, so our new generic DR models. And before I continue, I would like to ask you one more question. So we'll have one more poll. Would actually like to learn which version of THCC you use at the moment. So I'm gonna launch the poll and wait for 10-15 seconds, give you time to give us the answer. Okay, I have to admit that I'm a bit surprised by the answer. So I'm going to close this poll shortly. So closing it and sharing the results. So as we can see, around 40% of you use actually the latest version. I'm a bit surprised. And then all the versions are represented 30%, and we can actually see that the even spread between 20.1 and 19.4. I'm a little bit surprised because we're all engineers here, and I know that we tend to avoid fixing things that are not broken. And in a way, today our role is actually to convince you that here we have a valid exception to that rule. So yeah, with that being said, let's start with our presentation. Actually, I'll have only one slide here, so I really want to make it interactive, and actually I tend to actually show our new features inside our software instead of just talking about them. And also, some of the features are going to be covered in more details in the upcoming demos, so I'm not going to spend too much time on all of them. So in 2020.2, we have highlighted 6 new features. Starting with this new, the highest fidelity machine model that we have developed so far, so-called spatial harmonic model of the PMSM. So with this model, we are not only taking into account saturation effects, but also machine geometry. So Peter will tell us and show us more in his demo. With 2020.2, this is a really actually nice addition to our software. Now we also support Linux. So if we go to our download page, we can actually see that now 2 installers are available. Windows as usual, but now also there is Linux version available for download. And you can actually quite easily tell that it is still in beta mode, meaning that some of the advanced features are not yet incorporated in our Linux version. In most cases, those are features that require additional files in our models. So the JMAG machine model that we're going to present today is one of the examples. So it's maybe not yet ready for some heavy-duty use, but I would say for most standard applications, it should be stable and complete enough. And with the upcoming software versions, we are going to actually make sure that Linux version has all the functions and features that you are used to with our Windows version. Okay, moving on to our next feature. Actually, we have added or completed, to be more precise, a microgrid library by 2 additional generic DR models. Here we talk about new diesel genset and wind power plant models. So my colleague Dusan is going to actually demonstrate use of these new components in his demo. So I'm not going to spend too much time on this. Our next feature added support for voltage drop modeling. For now, it is supported on our most commonly used 2-level converter models. And it is important to point out that it is actually natively supported by our FPGA solver, meaning that it's running at full simulation resolution, basically the fundamental simulation step. So actually we have really high resolution simulation of that effect. Again, it's going to be shortly demonstrated by Peter in his demo. And then the next feature I'm going to spend a little bit more time on is the official support for external C code generation, so ability to generate code from our models. And I'm actually going to demonstrate this quickly. So I'm going to move on to our schematic editor. And there I have a model actually opened. This is one of our example models, relatively advanced motor drive model. So we have a rectifier, inverter, but then we also do fancy things like power loss calculation, efficiency calculation of the inverter. And then we also do thermal model of the machine and then its impact on stator resistance. So this is basically our standard example model. You can open it and run it for yourself. This is the name of the model. But in this example now we are going to focus on code generation feature. So code generation, we can actually generate code from our signal processing subsystems. And for now, we are limited to subsystems with only 1 execution array. So what I'm going to do now is I'm going to generate code for our controller in this example. It's relatively simple, but maybe enough to demonstrate the functionality. So by doing right-click, we can see that we have a new option, C code export. And let's first configure the code exporter. So there are very few options, as we can see now. We can select the folder where we're going to generate our code, and we can do type mapping as well. With type mapping, we can actually define how we're mapping our internal types to the types that are going to exist in the generated code. So we have only 3 types available: integer, assigned integer, we call it print, and real. So by default, they're going to be mapped to integer, assigned integer, and double C types. We can, of course, override this if needed. So we can even use custom types that might exist on our platform. So for this demo, I'm going to keep it simple, keep them all by default, or probably double. All right. And let's explore the code. So it's going to take a couple of seconds. Yeah, and after this is done, our code should actually end up in this folder. Actually, it's named by the subsystem name, so inverter control in this case. And if we open it up, actually you can see that we have 3 files, so C file, in which we can find our step and init function. And then we have also our H file with type definitions and input-output state structures. So let me open it up as well. So this is a standard NCC platform agnostic code that you can pretty much use on any platform. So the only customization available at the moment is the ability to define type mapping from our internal types to the C type that are going to exist in the code. So yeah, moving on to our next feature. Yeah, one thing that is also important to mention here is actually that code generation is part of our standard package. So no additional toolbox is needed for this functionality. So even in the free version of our software, you can access this function easily. And the last one in our highlight section is the nonlinear motor model that we can configure using JMake RTT files, so files exported from JMake motor design tool. Peter is also gonna demonstrate usage of this new component as well in his demo. We would also like to take you through to some of the general improvements of our software that we also mentioned in our release notes. So this list is nothing more than a snapshot from our release notes document. When we introduced HIL 404, we mentioned that we have adopted a completely new processing platform that has multiple CPUs available, but so far these were not available or user acceptable. With 2020.2, actually, we have made those extra CPUs available to our models. I'm going to just quickly demonstrate actually how we can make use of them from our models. So going back to my schematic, and I have a simple model to demonstrate this new feature. At the moment, I also have a 404 on my table running this model at the moment, and this model uses generic microgrid DR components. So we have a grid model together with a PV power plant model and a battery ESS system model. All these components, as it's going to be better explained by Tushan later on, typically run at two execution rates. So in this case, 100 and 500 microseconds. So, and if I go to HIL SCADA, I'm gonna start this model. So I'm not really going to focus that much on model operations. So I'd just like to highlight the code execution on the CPUs. So if we go there, actually we can see at the moment, as we expect, that the model is running on a single CPU at 2 execution rates, and we can actually see a time plot utilization on them. So how can we actually utilize those additional CPU cores? Actually, the moment we have 2 available on a HIL 404. Actually, there are 2 ways to do that, and I'm going to demonstrate a very nice way to do that. It will actually will not require from us to make any changes to the model at all. So going to schematic settings, and what I'm going to do now, so if our machines support multiple CPUs, we are going to have this option available. So CPU mapping option is right now at default. I'm going to actually switch it to this option, execution rate based. With this, actually our compiler will try to distribute workload among different CPUs based on different execution rates in the model. So actually, with this we will expect actually to have one execution rate running on one CPU and the other one on the other CPU core. No need to, again, to make any changes to the models. It's a very convenient way of distributing workload in models that actually have multiple execution rates. And in the case we had more execution rates, actually, again, we would assign them in the ascending order. So first one will go to the first CPU, second one to the second, and so on. Okay, waiting a little bit for the model to be compiled. And meanwhile, I'm going to stop our model, or maybe we can run it a little bit more just to emphasize that at the moment we are using only one CPU, actually running 2 execution rates at the moment. Okay. Okay, almost done. So yeah, for some reason my computer is running really slowly. Yeah, hopefully it's gonna be done soon. Yeah. Okay, waiting some more. Yeah. It should normally be much faster, so but I guess it's Murphy's law. So we can actually see that now the code is being compiled for 2 CPUs, so CPU 0 and CPU 1 at the moment. And, yeah. Okay, well, yeah, it's fine there. Reloading the model to my HIL 404, starting the simulation again, so you can actually see the same response, so no surprises there. But if I go to my time slot monitor, now we can actually see that, again, we have, of course, 2 execution rates as defined in the model, but actually we can see that the fastest execution rate is executed on the CPU core 0, and the 500 microsecond one is running on another CPU. It's a very convenient way to distribute workload with our models. Of course, in addition to this, we can have much tighter control of CPU partitioning. So by using default CPU mapping and those dedicated components, so CPU marker component is there to mark a group of components that we want to place in a certain CPU, and to connect groups of components that are running on different CPUs, we use CPU transition components. So very similar to what we do with device partitioning as well. I'm not gonna cover that part in this demo. So yeah, going back to our list, the last highlighted feature is this support for, as I mentioned, JMake. Sorry guys. Actually, another thing that I would like to mention is that with this software version, we have also slightly improved signal processing performance of all our devices. And this is also the case with the older machines that we support at the moment, HIL 600 and 602. Actually, here we're focusing on CPU performance, so signal processing, and this speed up can be anywhere between 10 and 40%. So it's significant, actually, can be noticed, especially in models that have a lot of interaction between the CPU and the FPGA part of the model. And with this, let me just open up our release notes document, so and show you how you can access it. So from our software, you can do that quite easily by clicking on the version link. So by clicking, actually, we can access the full list of features that are added. Another way, of course, is also to do that from our download page. There is also a link here. So yeah, there we have a full list of features available. But I would like to say, especially in case of this software version, there's even more. So with this software version, actually, we have just one data point. We have actually fixed more than 150 bugs reported on our issue tracking system. Those are all minor issues, really, but they really add up. And I think that they together really improve user experience quite a lot. So even if you're not maybe that interested in the features listed here, you still might benefit actually from all these tiny improvements they're probably going to make your life much easier on a daily basis if you use our software that frequently. And of course, as we mentioned, there is always that risk with upgrading to the new software version. And I would just like to mention here that we really take backward compatibility very seriously. We have an extensive list of regression tests that we do very frequently in order to ensure actually that every new software version is going to be able to run models created in the previous one, and actually the models are going to behave the same. This is quite important, and whenever we make a backward compatible change, it is always listed in our release notes. Actually, with this version, there are no such modifications, but if you are forced to make them, they're always listed here. And one more of a reminder, actually, is that since 2019.2, it is actually possible to have multiple software versions installed at the same time. So it is actually quite easy to install new version, give it a try, and if you run into any issue, you could very easily roll back to the previous version you used. And of course, if you run into some issue, we would really like you to tell us. So by going to our support portal, actually, it's very easy to create new tickets to really help us, tell us about the issue that you're facing, give us a chance to fix it promptly. Or if you would just like some assistance from our customer support team in model creation or test automation or whatever it might be, would really like to basically contact us using this portal. Or, for example, if you're interested in a new feature, this will also be the right place to request them. So with that being said, I would like us to move on to our first demo. But before we do that, we have another small question. So let me just start it quickly. And we would really like to learn which of the features that we covered you really find most useful and most relevant for your use case. All right, thank you all for participating. I'm going to slowly close the poll and share the results. So I think that we have a clear winner. It's a C code generator. I'm a little bit surprised. Then closely followed by new additions to the microgrid library, and then induction motor with volt injection. So with that being said, I'm gonna hand over control to Petar, who is gonna tell and show us more about new advanced machine models. So Petar, I'm gonna pass control over to you. The floor is yours.
Okay, guys, so do you see the screen? Just need to, okay, great. Okay, first, just a couple of slides about the machine features. So we're going to show three things. The first is going to be the permanent magnet synchronous machine spatial harmonic model. So what is it? It's basically a high fidelity model of a PMSM, which considers the effects of machine geometry on the fields inside the machine. So flow, fluxes, also on the inductances and the torque. So a little bit more details if we take a look at the picture on the right. So if we consider only the saturation, we can see clearly that the torque versus current curve has a linear region over here, and then we have the saturation region after it when the current goes really high. But with the spatial harmonics model, what we also do is we introduced another dimension to our model, which is the spatial component. So what happens here is that as the machine spins, we basically have the torque value oscillating around some average value, depending on the rotor position. Now, these models are highly detailed, and they're usually made from finite element analysis tools. So, you know, in order to integrate better with such tools, we've started collaborating with JMAC, which is an FEA-based tool that generates a high fidelity plant model, specifically electrical machine models. And the idea here is to generate the high fidelity motor model, import the file into Typhoon, and just run it in the simulation. So it should be seamless from one software tool to the next. And I'll show this as well. And finally, I'm going to show the fault injection into the induction machine. Specifically, we are going to cover the interturn short circuit fault on one of the stator windings. Okay, so I'll jump to my schematic. So I have three schematics prepared. The first one is the PMSM drive with the spatial harmonic PMSM model, and these effects are parameterized in the Typhoon model using lookup tables. So specifically here we have three lookup tables. So two for the current tables that are functions of the fluxes and the rotor position, and we have the third table that is the torque table, that is a function of the currents and the torque position and the rotor position. Now the model is relatively simple. So we have a DC link battery in the DC link. We have a somewhat detailed switch models that consider the forward voltage drop and also the switching losses and thermal effects. All the switches are characterized using the XML files, which we actually downloaded from the semiconductor manufacturer website. So this is just an example. Now, this is quickly about the model. I'll jump into the SCADA. So what we have here, we can set the speed reference for our controller, and I'm going to start the simulation. So the model is actually running on a HIL 404 with a 500 nanosecond time step. So I started the simulation. I'll give the speed reference to the controller. I'll set some torque load for the motor. And first I'll just show the effects of the forward voltage drop. So what I'm showing here is the gating signals for the leg in phase A. I'm showing the DC link voltage and the A phase to negative DC link voltage and phase A current. So we can see that when the current is positive, we can see actually that the phase voltage to negative DC link is actually not equal to the DC link voltage, but it's somewhat less due to the forward voltage drop. And we can clearly see that it's not only a fixed voltage value, but it also depends on the current. So the higher the current, the larger the voltage drop. And similarly, if we take a look at our negative edges, we can see that when the lower IGBT conducts or diode, the voltage from A phase to negative is not actually 0. Okay, and for the default, for the effects of the spatial harmonics, I'm just going to capture the signals. So I'm capturing the currents, D and Q axis currents, the electrical torque, and the machine speed. And we can see some of these oscillations come from the ripple effects of the switching. Some come from the controller parameters themselves, but these high oscillations are mostly due to the spatial effects in the machine. So you can see that the torque is oscillating around 50 Newton meters that we've set as the load, but it's got really high oscillations. Okay, so this was shortly about the spatial harmonic. I'm going to show the JMAG model next. So since this is a PMSM, again, the model is going to be the same. The only difference is that the actual effects, either saturation or spatial harmonics, are parameterized using the RTT file, which are generated using JMAG RT. Now, for this demo, we are going to use the LDLQ table model, which only considers the flux saturation in the machine. So I'll stop this model, load the compiled JMAG. Yes, and since the PMSM machine that we used is actually based on the same, the model that we use is actually based on the same machine, I'm going to give it again the 600 RPM reference and 50 Newton meters torque and see what we get with only the saturation mode. And you can see, especially in the torque, that now we have much smaller oscillations here than we had in the spatial harmonic model, and this one only considers the saturation. All right, and finally, I'm going to show the fault injection in the induction machine. So from 2020.2 release, the induction machine with squirrel cage has an additional property tab, which you can use to parameterize your fault. So at the moment, only inter-turn short circuit is possible in a single phase of your choosing. When it's enabled, another port will appear here that parameterizes our fault. Basically, what we can do is set the severity factor and the fault resistance. The severity factor being the number of short-circuited turns divided by the total number of turns in a winding, and the fault resistance is the resistance of the fault. Now, these two can be changed during the simulation runtime, so we can simulate the gradual progression of our fault and see if we can catch it in early stages. So I'm going to load this last model, load the SCADA as well. Now I'll start the simulation. What we have here is open loop, it's not open, closed loop V over F control of the induction machine. At first, we have zero severity and some whatever fault resistance. So we have a healthy machine. We observe the IGBT junction temperatures here, and we can observe the speed over here. So I'm just quickly going to capture the data to see what it looks like, so we can see the currents, torque, and the speed. Now I'm going to set some 1% severity factor for the fault and some small fault resistance. See what happens. Now, when we just capture the data, it might not be as obvious, but I think if we increase the faults are more, we're going to see first of all in the IGBT temperatures that something's going on. And now we've increased the fault severity to 5%, and we can see, maybe not so clearly from this capture still, but we can clearly see that the A phase current is larger because of the higher temperatures of the IGBTs. And now we see that we have some higher oscillations in the torque here and also in the speed. And now I'm just going to go to a bit more extreme case just to highlight this to see what happens. So we can see that now we have 10% severity factor and 0.01 ohms resistance. We can see the current, the temperature increasing even more. And if we now capture the currents, we can clearly see that our induction motor is obviously no longer a balanced load. So high oscillations in the torque and obviously higher current in the short-circuited winding. So this was from me shortly. If you have any questions, just please ask, and I'll hand it over to Dušan next.
Okay, thank you, Peter. Just to share my screen. I think that this is the option. Okay, probably you can see my screen. Yeah, great. I'm going straight onto the model, and I will show you an off-grid system that consists of basically these new DR generic components. So on the left side, we have, let's say, power generation part, which consists of diesel genset and the PV power plant. And on the right, we have the load part, which consists of constant impedance load in this case. And also we have included here battery ESS system in order to make this whole off-grid system more efficient. Okay, so power ratings, basically the load is 0.5 megawatts, and this battery is 200 kilowatts, so it's not sufficient basically to support this whole load. So in any case, either diesel genset or PV power should be on and providing power to the load. Okay, so these are the new generic components. They consist of two parts. Basically, the main part is the DR model itself. So if you go on the mask, these components are really easily parameterized, basically just with nominal parameters. All these nominal parameters are then used under the mask to parameterize first the power stage, and then to parameterize the inner control loops that are necessary for DRs to operate. Okay. Also, what is interesting, in all of these DRs, we have embedded transformers. So, for example, in this particular example, for example, this nominal generator line voltage is 400 volts, but we are boosting that to 10 kV. So this line here is all 10 kV. Okay, so also the similar story is with other DRs. So nominal values on the general tab. Then the second tab is more related to DR, specific DR model. Then we have this extra tab where you can basically in per unit values parameterize power stage in a way that it is more closely to your application or your system that you have. In this way, we can bring this generic model closer to basically to your needs. Okay, that being said, let's briefly introduce the UI components, which are also really important. So basically, if we go inside the UI components, we have all commands listed here, with these SCADA inputs. And also on the left, all the, for example, measurements that are coming from DR are here, then some statuses, feedback signals, nominal values are listed here, and so on and so forth. These UI components are meant to be unlinked and changed by you. And I will show you, for example, here how we did it. And we actually inserted the Modbus Sunspec Modbus server inside the UI component. So this is a PV UI block. And actually this PV power plant will be controlled actually from the Modbus directly. So the idea with this UI component is basically so that you can easily insert, for example, your communication that you want. Make small modification in terms of signal values or signal types. So you can connect these output signals from the DR with the communication server, or also send the signals from the communication to the actual DR and control it in that way. Then the battery ESS is again controlled from the SCADA inputs directly, so no communication protocol involved here. So this model is already compiled. I'm having here with me 404 unit. So, and let's go to the SCADA and see how this system actually works. Okay, so the SCADA panel consists of two sub-panels. One sub-panel is basically related to diesel genset component, and another is battery for the battery ESS. If I go inside, here we have the widgets and measurements basically that are coming from generic diesel genset model. And all these widgets here are basically connected either to probe signals or either to SCADA inputs. So we can directly from this sub-panel control and observe what is happening with our diesel genset component. Okay, the similar story is with the battery ESS. Okay, so what is nice about these sub-panels, they are already included in our example model. So you can basically just open our model, copy it in your SCADA, parameterize it in a way that you just have to, in the local namespace, add the name here for your UI block with a dot at the end, and you're ready to go. Okay, then on the right we have the group of widgets which is related to PV plant. Here, because we are using the Modbus, actually we are simulating the Modbus client directly in our SCADA, and basically then sending the commands to the Modbus server and then to the PV power plant. Okay, and the central part of the SCADA is basically trace graphs where we can observe the power flow into the system and how the frequency is changing. Okay, let's run the simulation. Okay, so right now with diesel genset is turned off. Basically, we don't have any voltage power. PV says that grid voltage is out of range. This is the fault. So this DR also supports some faults and also state machines. So they represent more and less real behavior or the real DRs. So let's, for example, enable diesel genset here in the droop mode of operation with the active power reference of 0.2 per unit, and here are the droop parameters. So now we can see that basically diesel genset took over the load. Let's go here and see on these graphs. So there was frequency dynamics. Okay, and now our frequency, because diesel density is working in droop, we have frequency that is close to 50 Hertz, but not exactly 50 because of the droop characteristics. Okay, now, for example, we have a voltage that is built from this diesel genset. Now we can, for example, reset alarm here. Now we don't have that fault anymore, and now this PV plant can be started. So first I will, because this is using the communication, I will first initialize the registers inside the Modbus Modbus server, yeah, with the values already presented here. So now we have the valid values for rate of change, for example, references and so on. And let's start the PV plant. So I'm enabling it, and now we can see basically how the power increased on the PV. PV active power increased, and basically this induced that the diesel genset now is supporting less of the load. Okay, so what we can do, we can basically, I don't know, for example, change the reference here for the active power limit, increase the PV power into the more PV power into the system, and also we can maybe support the system with a little bit of reactive power. So let's say 0.2 per unit, and now also here we can see because of this reactive power that our voltage on the bus increased a little, which is expected. Also on the graph on the bottom, we can see some dynamics in the frequency due to changes that we introduced in the system. Okay, now we will start the interesting part. For example, in starting the battery in droop mode. So battery will be working in parallel with diesel genset in the droop mode of operation. Okay, now we see that our state machine, actually our DR, is in the running state. We had some transient here, and we can see here that actually battery is supplying the load with almost 10 kilowatts. Okay, the frequency now is a little bit different than previously, but this is also expected because now we have two DRs in parallel with different droop characteristics. Okay, we observe here some changes. And now, for example, what will be interesting, maybe to increase a little bit PV power in the system, because here you can also see that available power from the PV is 1.2 megawatts. So we have plenty of PV power at our disposal. So we will increase the active power limit, and actually now the power from the diesel genset decreased. So the value of that power is around 50 kilowatts. So this diesel genset now is operating a low power regime, in which is the least efficient. So let's say that this power of 50 kilowatts, we can transfer it to the battery, and we will at this point, for example, just disengage this diesel genset. Okay, I've done that. We can see now in the system basically that our frequency dropped below 50 Hertz. Okay, diesel genset active power dropped to 0. That's expected because we turned it off, and that means that our battery took over that power to supply the load. And that is actually the case. So right now we have our battery that is discharging. You can see here how state of charge goes down. That's fine. And now we actually have a system where we have a battery and PV supplying that load. So diesel genset is not working. Now what we can do, for example, is reduce the irradiance of the PV panels, and let's say that we are below this limit that we have of 400 kilowatts. Okay, maybe something like this. Okay, and now you can see that active power produced by PV reduced to this available PV power here. So now the power of the battery increased, okay, due to that. And for example, we are not comfortable now to to engage to have a battery operating at this high power to that, because and in a case, and now we can maybe again include the diesel genset into the system. So it is in the droop mode of operation. Okay, let's enable it. Now from disable state, it is in the syncing up state. Now it's syncing up. Let's wait a little bit. And now it is in the running state, and we can see that the diesel genset took over some power from the battery. That's expected. Okay, and the took over battery, and the battery power dropped. Now, because battery is at like low state of charge, let's say like that, we can, for example, say that we want to fill this or to recharge the battery, and we can, for example, put here active power reference to negative. That means that we want to charge our battery. Then we can see here the response of the battery power, which become negative in this case. In this case, frequency is 50.4 hertz, and the diesel genset actually took over, and now we are basically charging this battery from the diesel genset. Also, what is interesting here, when we increase the power of the diesel genset, we can also see how the frequency dropped and then eventually went to the steady state, which is defined by the droop characteristics. Okay, so I would say that this is it from my demo. Yeah. Taking over to you, Matt.
Thanks, Dusan. And Dusan M, I think we have some questions to go through, and
Sure.
we have just a few minutes. We may have to circle back, but we've got about 3 minutes if you could just take a quick look at them. And I can, there's one on the SunSpec Modbus functions regarding the PV plant implementation, and I know communications is a big piece. I think Dusan C, that's really to you, is how do we do the SunSpec Modbus functionality in our generic models?
So basically, Modbus SunSpec components is available in our library. So the only thing that what is necessary basically is first to unlink.
Maybe propose that you share the screen if possible.
Yeah, sorry, just a second. Can you see it? Yeah.
Yes.
Okay, great. So first, what is necessary here is basically to, for example, you want to add the Modbus SunSpec into the diesel genset UI. So the first thing you should do is to unlink the component. That means that you can now change the internals of it, and then into our library, just search for Modbus, and then you will have the component, and then insert it here and start adding your models or whatever you basically build your communication from it. Also, we support a lot of communication protocols. Here I will just open it, and also, yeah, we are adding new ones all the time.
So thank you, Dusan. And I see another question. So thank you guys for asking all these questions. So the one is referring to the PWM modulators. The question is, how many PWM modulators do we support on our devices, and what is the maximum switching frequency of our PWM modulators, and again, what is the shortest time step we can support? So speaking about PWM modulators, thank you, Dusan, for your assistance. So in most of our devices, we support up to 12 individual PWM channels, as mentioned here. You can actually see the exact number on each device in the device table as presented here. So the maximum switching frequency, I believe starting with this version is 500 kilohertz for all our PWMs, although time resolution differ from device to device. So for example, for HIL 404, PWM resolution is around 3.5 nanoseconds. So this is actually the counter period. And in terms of simulation steps, again, depending on the device, but if you talk about HIL 404, which is our most recent and fastest device, simulation step can go all the way down to 200 nanoseconds. So you can either go auto or kind of explicitly select the one, so we can go down to 200 nanoseconds. Again, depending on the model complexity, of course. I hope this answered the question.
Well, we're coming up on the end of our hour. We've actually already hit it. I want to thank everybody, number one, because I know people will start peeling off. We can remain on for a couple more minutes just to wrap up if anyone has any specific questions. But I want to emphasize this is our first time we've kind of had an interactive webinar for our Typhoon HIL Control Center updates. Your input is absolutely critical to us, both to make future events like this better, but more importantly, to tell us what you think we need to be doing as we go forward. And so I ask that you take a few minutes to do the survey that you'll get via email. And just very much, again, want to thank everybody. And I also want to thank our panelists. And it always impresses me, our engineering expertise at Typhoon. Of course, that's what we're about. So thank you, gentlemen. And Dushan, any last words from you, since you're the chief technical officer for our outfit?
It was really a pleasure, and it's great for us to have this opportunity actually to share the results of our really hard work regarding all our new software versions. And I hope that we're going to make this webinar traditional, and basically to really enjoy this opportunity to share what we've done. And of course, thank you for asking all these questions. And I just want to say that all the questions are going to be answered, and those that we couldn't address today live are going to be, of course, addressed offline. So thank you all once more for attending.
Dushan, what do you think about, I think the audience is starting to leave. Some of the people who asked questions have already left. But one thing we could do is just kind of go through these questions, that way they'll be recorded. Do you think, just if you want to hit on a few, it looks like we might have lost audio there, though. Webster, I see your comment.
I'm still here, so I hope you can hear
yeah,
me.
I hear you. So maybe I see we have one from Habib at Solar Turbines regarding changing voltage on the new genset. Maybe we could just go through these real quickly. That way they'll be in the recording.
Absolutely. I think that this question is more for you, Dushan. It's a little bit confusing. We have two Dushans here today. Yeah, is there a way to change the nominal voltage? So maybe you can even show how this can be done in the new models.
Yeah, sure. So changing the nominal voltage of the diesel genset, and that was the question, I think.
Yes.
So basically, basically, just on the mask of the component in the general tab, basically there are two voltages. One is nominal generator line voltage. So that's the parameter that you should basically change according to your needs. And also, because here inside we have the transformer, you can also specify the grid line voltage, and that is the parameter just underneath this one. So the nominal voltage values are changed basically directly on the mask of each DR generic components. So it is the same for others as well.
Yes, so the next question we might take, and this is a complex one, we get this question quite often, and it's probably not an easy question to answer. So is it planned to have in the near future an automatic core coupling placement? So as we know, our FPGA solver is a multi-core platform, and each core has somewhat limited capacity in terms of number of inverters that it can support or overall model complexity that it can handle. So meaning that in more complex models, we typically need to partition our circuit into smaller submodels. And I would say this process requires a little bit of kind of knowledge of the details of our modeling approach. So the question was, are we working actually, and if we do, when do we actually plan to have this fully automated, meaning that our users do not actually need to care about model partitioning. So instead, our compiler would be smart enough to place those core couplings, or actually to distribute circuits model partitions on our FPGA solver cores. And we are definitely working on this. And at the moment, we have to say this is still in the research phase. So it's still not something that we can share with our users. And hopefully, in a kind of midterm, we'll actually have something that we can offer that might prove especially useful in power electronics applications, where actually the high dynamics of the system sometimes can make placement of such components really critical. Yeah, maybe we can take one more. So there's a question about SunSpec. I think we kind of answered that one, at least partly, but the question was PV plant, does it, our PV plant model implements the full SunSpec modulus functions? So actually, maybe it requires a little bit of extra explanation. So if we enter inside, actually, so what we basically did, we have put our standard component from the library, modulus SunSpec component, and then basically it is highly configurable. So if we enter the solution already showed, we can actually add all these different register banks that are defined according to SunSpec. So we can really configure it the way we want, and we can even add standard models, common model, but also vendor-specific models, as we can see, can be added as well in a model. So in that regard, we can really configure it in any way necessary to emulate, I would say, just any modulus SunSpec compliant device that we might use.
So a lot of options here.
Yes. And basically, this communication component can be hooked up to just any DR model. It's not, of course, limited to our PV plant model. It can connect to DG or ESS system or wind power plant as well. So it is quite configurable and flexible. Okay. So one question, is there a reference for the load impedance range?
Load impedance range. Okay. So basically it's parameters here on the mask, and it's 0.5 mega volts amps with the power factor of 0.9. So a lag. So this is the specification of the constant impedance load, if that was the question.
Can we maybe comment a little bit on different load types that are supported? Maybe this would also help clarify that one.
So right now we have, if we go here, we have this VBR variable load, but in the next release we will include the generic variable load that will be in the same frame like these existent generic DR components. So we will add we will add the variable load generic component in the next release that is already implemented. But for now, in this release, for example, if you want a variable load, then you should go with VBR variable load component. I can just drag and drop it here. So yeah.
So thank you, Dusan. One more. I think we have partly answered this one, but let's also take it. So frequency and time step that your system can handle. I think that we mentioned the time step piece, and if you talk about frequency, I believe it means switching frequency that our system can handle. And this is a great question. So this is very specific for our system because we can actually handle switching frequency that's much higher than what our minimum simulation step would suggest. So at 200 nanoseconds, and say if we are targeting 8-bit resolution, we're going to be limited to somewhere around 40 kilohertz, probably not more than that. But actually, as was mentioned before, use one special technique called GDS oversampling, where we actually sample our digital inputs actually much faster, again, depending on the device, but going down to 3.5 nanosecond sampling period. And then we actually timestamp all the switching events on the inputs, all the transition of our gating signals. And we use that timestamp information to compensate for the integration error that is coming from this relatively low simulation step in relation actually to the PWM switching period. So our effective resolution is much higher than our simulation step would suggest. So we've seen applications going all the way up to 200 kilohertz done with our system in, I'll say, this typical real-time operation mode. There is also a way to do time step scaling. Then we can go even higher, but I would say with pure real-time setups, we've seen applications up to 200 kilohertz being handled by our devices. Okay, and
we have a few who have stuck with us throughout. Dusan, I see. I think you've covered the questions, but I want to make sure. Did we do Ivan Todorovich's question? Would it be possible to detect the slots induced harmonics in the DC link voltage? Do you see that one?
Yeah, I missed that one. I'm trying to, yeah, maybe better this one is more for you.
Yes, just a second. Okay. Okay, so yeah, I was actually wondering, well, I read the question. So let me just share my screen again. Okay, not sure which screen is showing.
Yeah, we can see your signal analyzer at the moment.
Okay, exactly, great. So what I did, I just did two captures, like the ones I showed in the demo. And I captured the DC link current actually. So this is the spatial harmonic case, and this is only the saturation case. And it's obvious that at least in the current, the dominant ripple is coming from the switching actually. And then I just did an FFT, and this one, okay, so the left one should be for the spatial harmonic model, and the right one should be for the saturation model. Yes, so for this specific model, then it clearly doesn't propagate, but I would say it also depends on the control parameters on the machine itself, on the switching. So I would say in general it could be noticeable, but it really depends on the system.
Mm-hmm.